Hi all, welcome to the fourth video on the problem set 1. We are discussing the electric field, electric force, the electrostatic energy stored in the configurations because of the point charge and the continuous charge distribution. In problem number 4, we are going to discuss how to calculate the electric field because of the line charge, circular line charge loop at a distance uh, g above the the plane containing uh, the circular loop xy circular loop which is carrying surface the line current lambda. So yes, we have to calculate the electric field because of this whole loop at this point here. We can use the concept of symmetry if you look here properly, and let me take, if I look only the electric field because of this small portion, the charge of this small portion, let's say if length is dl, then the charge present in this small length is lambda dl, and this charge gives the electric field at that point. And the electric line of force goes something like this, right? So it has horizontal component as well as vertical component. So it has one component going inside going inside the plane of the paper. So it has three components and the resultant is on this side. But if we take the electric field because of the whole, this component will be cancelled because of the symmetry. Similarly, if we take explain this fact by supposing this small element dl here again. If it is dl, its charge is lambda, then the total charge is dl lambda of this small portion just opposite to this one, 180 opposite. Then the electric field because of this would go something like this, and it has this component and the one component coming outside, right? One component coming outside. So the original component provided by this element is in opposite direction to the horizontal component provided by this element in this direction. Similarly, one component is going inside because of this, and the one component is coming outside because of this. So these two are also cancelled. In total, if we take all the small elements at a time, because of the circular symmetry, all the horizontal components cancel each other, and only the vertical component, this component, will remain. Finally, they will add up. So we'll be only looking on the g component or the vertical component of the electric field because of the entire loop. So let's move ahead. Before going there, I would like once to uh, let me just clear this. Okay, I have this. Then yeah, in question number 2, we'll be discussing about the you can see here, we'll be discussing about the uh, non-uniform charge distribution. In this case, the lambda is same as we go from here to here. Lambda is the charge per unit length is same, but in this case, charge per unit length is changing with phi. Here phi is the angle with the horizontal sorry, with the x, and it moves something like this up to 2 pi degree. So the lambda is changing with phi. Here the phi is different, here the phi is different, here the phi is different, here the phi is different. Because of that reason, the charge per unit length also is different, so there will no more symmetry remain there. Its horizontal component and its horizontal component are different. They have different length, they're different magnitude towards the horizontal line, so we'll get effective component around the horizontal direction. So we cannot use the symmetry in that case if the charge is non-uniform. So let's begin this problem. Okay, so I have here uh, uh, circular This is the x-axis, this is y-axis. Okay, and let me pick this as um, and this as the small angle. Let me take this as the, okay, this is the small angle. Then let us say this is phi. Let me take this is phi. Okay, this is x, y, g. Let me take this is the small increment in the angle d phi. If I take this as the small element dl, here to here is the radius of loop r, then dl should be equal to r d phi, r d phi, right? So if lambda is the charge per unit length, then the charge contained in that small line element is dq, which is equals to the lambda into dl, or lambda r into d phi is the charge present here. So the principle is like, if we have to calculate the electric field at a distance g above the origin, which lies at the center of the loop, uh, we calculate the electric field because of that small element, and we integrate over the whole length of the loop. So let's begin. So how do we calculate? First of all, before going there, I write the position vector of a small element. Position vector of a small element, let me say position vector of source, a small element, because it is the source charge. Position vector in the this coordinate system can be written as r cos theta. Here I am using phi, r cos phi I plus r sin phi z. This is the position vector of the source, and the position vector of the destination point, let us say this point is p, let me suppose this point is p, is 0 into, sorry, x component is 0, it is on y axis, so only the z component survives, so it is along k direction. So electric field expression is always, in case of the charge distribution, electric field of, because of the small element, is dq k into r p of the position vector of the point charge, the the point where we are interested to find electric field, its position vector minus position vector of the source charge. This gives the direction, divided by rp minus rs whole cube. If you write here is square, here this vector, whole vector, would be replaced by the unit vector of the direction of the electric field, the direction of the electric field. So this time I'm going to include all the components. So I will calculate rp minus rs, which goes like gk minus r cos phi I minus r sin phi g, that's a c, and rp minus rs magnitude would go this square plus minus r cos phi square plus minus r sin phi square. So this gives me g square plus r square, and it is kind of interesting that for the particular j, this part is always constant. Wherever we take that small element, if we take here, it doesn't matter, because the radius of the loop is constant, and the g is at constant height, or constant height above the the center of the loop. Okay, now let's use the formula of electric field because of the small charge element is dE, k dq k, and the dq is, the dq is, here we have calculated what is dq is. Dq is lambda r d phi, and the difference of this position vector are this one, gk vector minus r cos phi I minus r sine phi and g over by uh, the cube of the magnitude of the distance between them. It is g squared plus r squared to the power 3 over by 2. Let me say this is the equation number D. Okay, so now we are interested in finding the electric field because of the entire loop. This is the expression of the electric field only because of the this component. It has three components. As I said before, uh, this line element gives the electric field, sorry, this is the straight line in all direction. This is the net direction, this is horizontal, this is vertical, and we have next component of horizontal as well on this direction acting inward to the plane of the paper. So we have three components, one on g, one on I direction, and one on j direction. But the horizontal components get cancelled each other because of the symmetry of the problem. It has circular symmetry, so the effect of this line element, horizontal component of this element, gets completely cancelled out by uh, the horizontal component of the element, which if we suppose just opposite to the loop uh, in 180 degree. So in order to calculate the total electric field and its direction, we integrate this one. So the total electric, let me change the color, the total, sorry, the total electric field due to the entire uh, charge loop is E equals to integration over dE from 0 to 2 pi r. 2 pi r is the length of the charge loop. So we look on the E equals to, here we can see these three are the constants, k lambda r, and this is also constant, this is not varying, z square plus r square to the power 3 by 2, 0 to 2 pi r, and gk minus r cos phi I minus r sine phi g over by g square plus r square, sorry, we have already written that, let me not include this part uh, here. Okay, yeah, oh yeah, I'm sorry, yeah, I forgot to mention this. Yeah, since we have taken the small angle element as the variable, so this one we have to take up to the r angle, phi angle increasing from 0 to 360 degree in the circular loop. So I am changing this limit, but because of the symmetry, as I explained before, this part would go 0 and this part would go 0, and in total I get k lambda r by g square plus r square 3 by 2, and g is the constant, 0 to pi d phi into k. It gives me k lambda r by g square plus r square 3 by 2, so into 2 pi g into 2 pi along k direction, right? So the answer becomes, so we get, let me write answer by like this, electric field equals to 2 pi g k lambda r, 2 pi g k lambda r over by r square plus g square to the power 3 by 2 is the electric field, and its net direction is along the z direction, or let's say I am supposing k direction along the z axis. This is the total electric field at a point z because of the circular loop. Now let's discuss the question number b. Question number b, here the condition is different. Condition is like, now we have not constant lambda. Lambda is varying with phi, so the charge per unit length here is different than charge on unit length here. So if we consider just opposite charge element, then its horizontal effect is not completely cancelled by this effect. The magnitude are different because of these cases. So we have to mention all the components. So let's begin the second problem. Here we have lambda is the function of uh, the angle, azimuthal angle, and this is written as a by pi r sine phi, q by sine r, q by sine, oh sorry, I'm sorry, q by pi r into sine phi. Phi changing with the phi changing with the azimuthal angle. So here what can we write is the problem is no more symmetric. The problem is no more symmetric. It has net horizontal components as well. So let's write again the expression of the electric field from here. Our electric field ADE is something like this, or better I would take the electric field, okay, I take it from here. I write it like, I have this electric field. But right now I have this lambda as a function of phi. I replace this. I have this lambda as a function of kr lambda of phi. I have this as a function of phi. So in order to calculate the total contribution on the electric field because of the whole loop, the x component and y component will no more be 0. So I'll be taking x component, y component, and z component of the electric field. It has three parts. Let me take the x part. Dex, I'm taking the x component of the electric field because of the small charge element. So it gives me that this is the x component. I take that part, k r square minus k, this r and r square lambda phi into cos phi into d phi over by r square plus g square 3 by 2. It is equal to, now we have the lambda phi. Lambda phi is equals to the here q by pi r sine phi, q by pi r sine phi. So I write minus k r square q by pi r sine phi cos phi d phi divided by r square plus g square 3 by 2. So yes, these r and r cancel, I write minus k r q uh, d pi by pi 3 by 2. So in order to calculate dE in total, so the horizontal component of electric field along x direction can be obtained by integrating all range over the all range for the x component. We get from here, if you look, the constant term are minus k r q by pi r square plus z square to the power 3 by 2, integrating over 0 to 2 pi d phi sin phi cos phi. Okay, so this integration is pretty easy. The cos phi is the even function, sin phi is the odd function, and we are in, so the total function is the total integrating, this part is total in is the odd function, so we are integrating 0 to 2 pi, so this contribution should go 0, so the ex part is 0. Similarly, we can look on the y component. Let me use different ink for y component. I'm using this green. Also, the dEy part, if we look from here, is this is the y part, this is the sin phi, so k r square lambda, it is also in the negative, minus k r square lambda phi cos phi, no sorry, sin phi, it is sin phi in the kth part, sin phi into d phi over by z square plus r square. It is the yth part. Let me check once. It is k r square lambda phi sin phi d phi by, okay. Now I am gonna replace the charge element, which is q square by, so k r square q by pi r sin phi into d phi over by okay. So now we calculate the total electric field Ey by integrating over the whole range. This gives me minus kq r by pi z square plus r square 3 by 2 0 to 2 pi sin square phi into d phi equal to this integration is okay. Let me do that integration in here. Integration over here, it is 0 to 2 pi sin a square phi into d phi equal to 1 by 2 0 to 2 pi. It is 1 minus cos 2 phi. We can replace this by 1 minus cos 2 phi into d phi. If we integrate over, we get phi cos 2 pi, and if we integrate, it gets minus 1 by 2 sin 2 phi minus 1 by 2 sin 2 phi over the range 0 to 2 pi. Oh sorry, what does it, yeah, it is something like this. Okay, cos 2 pi is sin 2 pi, 0 to 2 pi Mhm. So this in total becomes 1 by 2 into this goes like 1 by 2 into 2 pi minus 1 by 4 into sine 2 into 2 pi minus 0. This part goes 0, which is equal to pi. So I write it here as this whole is the pi, so minus kq pi by pi z square plus r square equal 3 by 2. So I get the white component in negative direction as z square plus r square 3 by 2. This part is along the y-axis. Similarly, I calculate the z component. Z component is, I'm going to use next ink for this one. Let me use this one. Let's calculate the z component. Here dez is this part. So rkg by r square plus g square to the power 3 by 2 lambda phi into d phi, which can be written as, so this gives me Ez equals to integration over 0 to 2 pi into deg equals to rkg of 1 r square plus g square 3 by 2, and we have the phi, so 0 to 2 pi sine phi into d phi, sine phi into d phi. Yeah, remember that this sine phi came from the charge distribution given on here, this part, sorry, this we have, oh sorry, I have q by pi r also here, q by pi r, q by pi r, this r and r cancelled out. So my electric field becomes k q g over by pi r square plus g square 3 by 2, and this integration is what? This integration is 0. This component is 0 because the integration over the odd function, so this is 0, gives me 0. So to get the net electric field, let me use the next pen here, the net electric field, sorry, net electric field at distance g above the plane for non-uniform charge distribution, which is ex plus ey plus ez, this along I, this along this along z. As we have just got above, you can see here our ex component is 0, z component is 0, we have only survived y component, so which is like this, z component is also there 0, so it should be something like k q r by g square plus r square 3 by 2 along z direction. So we have net electric field is this because of the non-uniform line charge distribution on the circular loop for this type of figure. So yes, we, if you look, we got entirely different expression here. When the charge distribution was uniform, we get only the g component, only the g component. Other two components cancel each other because of the symmetry. And in this case, in the given non-uniform charge distribution, as q equal to q by lambda equals to q by pi r into sine phi, here, because of the nature of the sine phi, we get only the horizontal component along the z direction or vertical, and the horizontal component on x direction gets becomes 0. Okay, so uh, this is all I wanted to discuss in this problem. See you in the next problem. Thank you.